Hi everyone. So in our last video, we learned about what an inverse function is. So in this video, we're going to continue to talk about inverse functions, specifically focusing on how to find the formula for the inverse of a specific function. So just to remind you of the definition of inverse functions, we learned this last time, which is that if f of x, so if you have a function that is a one-to-one function. So what is a one-to-one function? It's a function where every input has its own individual output. Or another way of saying that is that there's no repeated outputs. So for example, f of x is equal to x squared is not one-to-one because you could plug in -3 and +3 and get the same result. And just to remind you from the last video that the visual way of seeing whether a function is one-to-one is what's called the horizontal line test. So you can go back and watch that if you want to remind yourself how that works. So if you have a function that is one-to-one, then it has an inverse function . And that inverse function is called f inverse of x. So that little -1 is just a symbol that represents the fact that it's the inverse. And how does this inverse function work? Well, it basically reverses the roles of inputs and outputs. So if you're taking the inverse of some number b, and your answer is a, some number a, well, that's going to be because if you plug in a to your original function, you get b. So whatever is your kind of input and output for your original function, they're going to swap. The original output will become an input, and output will become input, input will become output. So just to remind you, one of the examples we talked about last time, so we had the function f of x is equal to x cubed. So that is a one-to-one function. It passes the horizontal line test. And so you have, for example, if you wanted to plug in the number 2, you would get 8, right? Because 2 cubed is 8. And so how would the inverse function work? Well, if you wanted to take f inverse of 8, your answer would be 2, right? Because working backwards, we know that when you plug in 2, you get 8. And so the reversal of that is you plug in 8, you get 2. And so what is the formula for this inverse function? Well, we saw last time that it is the cube root of x, right? Because what would be the function that when you plug in 8, you get 2? Well, of course, there's other possibilities out there, but what's the function that is always going to kind of work backwards compared to cubing? It's always going to be taking the cube root. And so that's the idea we're going to be focusing on in this video, is this idea that when you look at the formulas of inverse functions, they're going to be reversing each other. And maybe there's one thing that I should say that I'm not sure I explicitly said in the last video. Inverse functions are basically a pair. So it's kind of just a point of view, which one you want to call the original function. So in this case, I wrote down x cubed as the original function. And so the inverse function was cube root of x. But if I wanted to, I also could have said our original function is cube root of x. And then the inverse function would have been x cubed. So what I'm getting at here is that anytime you find the inverse function of a function, it's not like the original function and the inverse function are somehow different. They're inverses of each other. It goes both ways. So it's just kind of a point of view of which one you want to think of as being your original function. Okay, so this idea that I just said was basically that if you have a function and its inverse function, what is the relationship between their formulas? Well, they basically kind of reverse each other. So the formula for an inverse function is basically a reversal of the formula for your original function, f of x, right? It undoes it. It kind of reverses the process. However, most functions we're going to be dealing with are going to be a little bit more complicated than this one, right? X cubed and cube root of x, it's pretty clear that those are opposites of each other, right? They're very straightforward. But most functions are going to kind of involve more steps than that. And so we need to really know what does it mean when we say that these formulas are reversals of each other? So specifically, if you list out the steps that a function f of x takes or let me say it this way, applies to each input. And if you're confused what I mean by that, don't worry, we're about to do an example. But if you list out all the steps, so in this case, there's only one step, right? It's like, what does the function f of x do? It cubes. But you might have a function that cubes and subtracts something and multiplies by something. So you're kind of listing out all the different operations, basically, that your function is doing to the input. So if you list out all those steps that your function applies to an input, then the inverse function, it will reverse the steps. And additionally, it will reverse the order of the steps. So we'll see again what I mean by that in a moment, and we'll also see why is it, I want to explain a little bit more after we do our first example, why is it that we're reversing not only each individual step, but also the order of the steps. So don't worry, we will get to that. Okay, so let's say that we wanted to find the inverse function of the function f of x is equal to x squared minus 1. And so remember, x squared minus 1, any kind of parabola, any function that has a shape that's a parabola, it's not going to be one-to-one. So what we need to do is add something called a domain restriction. And so in this case, the domain restriction that would make the function one-to-one would be x is greater than or equal to 0. So I just want to remind you where that comes from. So this is a domain restriction. And so domain restrictions, the general idea is that if you take your original function, the one that is not one-to-one, so in this case, what would x squared minus 1 look like? Well, it would be a parabola that's been shifted down by 1, and so it would look like this. So how do you make this one-to-one? Well, you basically just kind of cross out half of it. So I'm just going to get rid of this half. And so what we're left with is only x values that are greater than or equal to 0. And so that's our domain restriction. And as I mentioned in our last video, we'll talk a little bit in our next video about what would happen if you tried to use the left side instead. For now, just know that the standard restriction that you're going to do for these types of functions is to take the right side of the function. Okay, so how are we going to approach this problem? So the first thing we want to do is we want to write down the steps that our original function f of x does to each input to get an output. So basically what I mean by that is, let's say you're plugging a number in, like let's say you're plugging 5 into this function f of x. What are you going to actually mathematically do as you plug in that number 5? Well, the first thing you're going to do is you're going to square it, right? You're going to square that input. And what are you going to do after you square the number? Well, then you're going to subtract 1. Right? If you plug in 5, you would get 5 squared, which is 25, minus 1 is 24. You would do the squaring first, then you subtract. So it's basically an order of operations kind of situation. So how would you then come up with the inverse function? Well, you want to take each of these steps and reverse them, but you also want to swap the order. And so the first step that our inverse function is going to do is it's going to reverse this step. So we're going to start at the bottom of the original list. So what would be like the reversal of subtracting 1? Well, to undo subtracting 1, you would need to add 1. And then what would be the reversal of this step? Well, if you're squaring something, if you want to undo that, what's the opposite of squaring? You would be taking the square root. Okay, so now we have a kind of list of what we want our inverse function to do. And what we can do with this list is we can now turn it into a function. So we're going to take these, think of these as like instructions that are telling us how to build this function, and now we just need to actually make it. So we want to make a function that takes an input and adds 1 and then takes the square root. So we have our input x. We want to start by adding 1, right? That's the first step. Then we're supposed to take the square root of the result, which means we want to take the square root of the whole thing, right? We want to ensure that first you're adding 1, then you're taking the square root. And that's it. That is our inverse function. And by the way, you do not need to put a domain restriction on this function because it's already one-to-one. So it's really only parabolas that we're going to be worrying about not being one-to-one. Of course, there's other functions out there that are not one-to-one, but for the sake of what the types of functions we'll actually be dealing with, it's really just parabolas that are going to not be one-to-one. Square root graphs are one-to-one, cube roots are one-to-one, cubes are one-to-one, linear functions are one-to-one, so you don't need to add domain restrictions for those types of functions. Okay, so why is it that we're not only reversing the steps, but also reversing the order of the steps? Well, there's an analogy that mathematicians like to use. I'm not sure where this originated, but if we're thinking of a function as a series of steps, and then we're thinking of the inverse function as undoing those steps, right? And so imagine that it's the beginning of the day, you're getting ready for work, and say you're actually working outside of the house. You first put on your socks and then you put on your shoes, right? Socks first, then shoes. And so how do you reverse that process at the end of the day? Well, you're taking things off now, right? In the beginning of the day, you're putting on your socks, on your shoes. At the end of the day, you're going to take off your socks and shoes, but what's the order going to be? Well, first you're going to take off your shoes and then you're going to take off your socks, right? You can't take off your socks first because your shoes are on the outside. And so that's really how these things are working. These functions are basically executing a series of steps, and those steps build on each other, right? They add like layers to your function. And so if you're trying to reverse the function, you have to peel back the layers one by one. And so you have to start with the reversing the last step and kind of work your way backwards. Okay, so we're going to do a few more examples using this method of kind of writing out what's going on in words. Just so you know, we will later in this video be also learning an algebraic method. I think both methods are really valuable. I've found that a lot of students actually tend to like this one better than the algebra. We'll see that there's some situations where you have to use algebra, but yeah, just wanted to give you a heads up that we'll be doing a few more examples like this, and then we'll see a different method as well. So in this case, let's find the inverse of a function that is going to seem really similar, but we'll see that there is a key difference. So the last function we worked with was x squared minus 1. This time we're going to work with x minus 1 squared. And so we have to add a domain restriction to this, right? Because it's still a parabola, it's still not one-to-one. So what would the domain restriction look like in this case? Well, what does the function x minus 1 squared look like? Now it's a parabola that's been shifted to the right by 1, right? So its graph would look like this. And so if we wanted to make this one one-to-one, we take away this left half of it. So in this case, because it's been shifted to the right by 1, our domain restriction would be x is greater than or equal to 1. So in this case, it was x is greater than or equal to 0 because that was where the vertex, where the center of this parabola was. Whereas in this one, because it's been shifted to the right by 1, that's why we need to say x is greater than or equal to 1 to get that right-hand side. Okay, so let's do the same idea. The first thing we're going to do is write down the steps that g of x does, then we'll do the inverse. So what does g of x do? Well, in this case, if you plug in a number, what are you going to do first? You're going to start by subtracting 1. Right? So in the last function, we squared first. This one, you're going to actually subtract 1 first because of the parentheses. And then you're going to square the result. And so what does that tell us about the inverse function? Well, the inverse function is going to start by reversing this step. So we're going to take the square root. And then we're going to reverse the next step. So what's the opposite of subtracting 1? It's adding 1. And so this time we're trying to cook up a function that first takes the square root of an input and then adds 1. So what is that going to look like? Well, that means we're taking the square root of the input, so that would be square root of x, and then we're adding 1 to the result. We're adding 1 after taking the square root. And so this is our function. So by the way, we can see that's different from the one that we got in the last one, right? So these were similar original functions. The first one was x squared minus 1. This is x minus 1 squared. And similarly, the inverse functions, they kind of look similar, but they're doing things in a different order. Okay, couple more examples. And I would encourage you, now that you hopefully have kind of a taste of how this works, to try some yourself. So try pausing the video and trying these examples yourself. So in this one, I want to find the inverse of h of x is equal to 2x minus 3. And we don't need a domain restriction for this, right? Because it's a line. A linear function is already one-to-one. It does not need any restrictions to make it one-to-one. Okay, so same idea as we did in the last ones. Let's start by writing down what h of x does, and then we'll reverse it. So if you're plugging in an input to this function, what's the first thing you're going to do? You're going to start by multiplying by 2. And then you're going to subtract 3. And so what is the inverse function going to do? Well, it's going to start by reversing the subtraction. So it's going to start by adding 3. And then it's going to, what's the opposite of multiplying by 2? Well, the opposite would be dividing by 2. So now we want to come up with a function that adds 3 and then divides by 2. So we want to take our input, x, and we want to start by adding 3. And then we want to divide that entire result by 2, and so that gives us the following. So by the way, if you wanted to graph this function, so this is something we'll get into in the next video, and actually on today's worksheet as well, I'll have you be graphing, how, my grammar is not coming out right. I will have you graph some functions and their inverses to kind of see what's going on as a preview for the next video. But anyway, if you wanted to graph this function, you might want to rewrite it slightly differently. So this way that we wrote it down here, the inverse function, it's good because we can really see what the steps are, but there's another way we could write this. We could split it up, right? We could rewrite this as x over 2 plus 3 over 2. And so what would be another way of writing that? Well, that's the same thing as saying 1/2 x plus 3/2. And so that would be our inverse function. So it's the same as the one we came up with. It's just kind of a friendlier version if you wanted to graph it, because now you can actually see what the slope and the y-intercept are a little bit more easily. Okay, last example. So this one's going to just be a tiny bit more complicated in that it will have more steps. And then it will also bring up something else about the domain restriction idea. So that's the other reason that I wanted to do this example. So we're going to find the inverse of the function k of x is equal to the square root of x plus 4 minus 3. So this one just has a little bit more going on than some of the other examples we did. So what are the steps that this function, the original function, does? Well, we start by adding 4. Right? If you're plugging in a number, the first thing you're doing is you're adding 4 to that number. Then you're taking the square root. And then once you take the square root of that result, then you subtract 3 from that. And so now when we do the inverse function, again, we're just reversing this list and we're reversing each of the steps. So we want to start by reversing the subtraction of 3. So that's going to be adding 3. Then we're going to reverse the middle step. So instead of taking the square root, we're going to square. And then we finally reverse the first step, which is instead of adding 4, we're going to subtract 4. And so we can put these together to write down our inverse function. So we want to take x, our input, and we're going to add 3, so x plus 3. We're then going to square that result, and then we're going to subtract 4. So there's one thing missing from this, which is that, remember that functions and their inverses, it goes both ways. So in order for either function to be the inverse of each other, they both need to be 1-to-1. So not only does the original function need to be 1-to-1, its inverse also has to be 1-to-1 because they're inverses of each other. And so we need to add a domain restriction to this function. And so if we think about what this graph looks like, well, this is one that is a parabola that has been shifted to the left by 3 and down by 4, right? So shifted to the left by 3, down by 4, so it's something like this. But the important thing isn't so much how much it's been shifted vertically. The important thing is that it's been shifted to the left by 3, right? Because really all we're caring about is where is this kind of starting point for the right half. And so because it's been shifted to the left by 3, that means that we want to make our restriction be x is greater than or equal to -3, because that's where that right half of the parabola starts. Okay, so as I said, I like this method a lot. I think it helps give you some intuition for like conceptually what's going on with inverse functions. It does have some limitations. So you might have functions that are a little bit more complicated, like they just have more steps than you really want to deal with. So personally, I think this method is best for when you have functions that only have a couple of steps. The other example I want to show you that really points out the limitations of this process is, let's say we wanted to find the inverse of the function, I'll call it L of x, is equal to x minus 2 over 3x plus 1. So functions that look like this are actually a little bit hard to figure out what the steps are, right? Because there's kind of things going on simultaneously, right? You're subtracting 2 from x, but at the same time, you're multiplying x by 3. It's like, how would you know which one goes first? And so basically, this method of writing out the steps isn't going to work for functions that look like this. So this method won't work. And so what we're going to learn is an algebraic method that we can use instead. So now we're going to be talking about, as I said, an algebraic method. So to help you understand where this algebraic method comes from and kind of why it works the way it does, I want to give you a little bit of a warm-up. So let's say that we have the function f of x is equal to 2x minus 3. So this is actually the same function, one of the same functions we worked with earlier. But forget for a moment what the inverse function is, right? We figured out the inverse of this, but erase that from your memory temporarily. So let's say all that we know is that our original function is 2x minus 3. And let's say we wanted to find the following two inverses. So I'm not going to be asking you to find the general inverse function, just the inverse of a particular value. So first one is f inverse of 7. And then let's also try to figure out what f inverse of 11.1. Okay, so maybe pause the video and think about how you would answer these two questions. Think about what f inverse of 7 and f inverse of 11.1, what do those mean? And how would you go about actually figuring out what they are? Okay, so what do these things mean? Well, f inverse of 7, if we go back to like the previous video, forgetting about formulas and just thinking about the definition of the inverse, f inverse of 7 is basically asking us to find some number a. So I'm just going to use a to represent some mystery number. And specifically, we want to find a number a such that if we plug that number into our original function, we get 7. right? That's how inverse functions work. It's basically asking us to work backwards. It's saying, I know the output is 7, find me the input. And so for this one, and this will not be the case for 11.1, but for 7, you might be able to figure this out just by kind of guess and check, right? So thinking about plugging in different numbers to f of x, what input would give you an output of 7? Well, if you plug in 5, you would get 2 times 5 is 10, minus 3, which is 7. And so that tells us that f inverse of 7 is equal to 5. Right? Because 5 is the, basically here we saw f of 5 is equal to 7, and that means f inverse of 7 is equal to 5. So what about this next one? So f inverse of 11.1, again, that is asking us to find some mystery number a, such that in this case, f of a is equal to 11.1. So this one I think you'd be hard pressed to do in your head, or maybe you can, I can't. I can't sit here and think of what is a value of x that would give me 11.1 as my output. So how can we figure it out without that? How can we figure out what x has to be without, or what a has to be without just testing out numbers? Well, what are we trying to do here? We're trying to figure out what input would give us an output of 11.1. And so how can we answer that question? Well, we can take our equation, our formula, 2x minus 3, and set it equal to 11.1 and solve for x, right? And if you don't understand that, pause the video and really think about it for a moment. I really, really want to make sure that you understand that step, that if you're looking for the inverse of a particular number, that means you're trying to find the input that gives you that number as the output. And so in general, if you're trying to find an input that gives you a particular output, well, you can take your function and set it equal to that output and solve for x, and that will tell you the corresponding input. So pause the video, make sure you really, really understand that line, because that's really important. And so now from here we can solve for x, right? And that will tell us what value of x would give us 11.1 as an output. So if we add 3 to both sides, we would get 2x is equal to 14.1. We could then divide both sides by 2. And so we would get x is equal to 14.1 over 2, which reduces to 7.05. And so this tells us that f inverse of 11.1 is equal to 7.05. And you could check that, right? You could double check that when you plug 7.05 into your original function, you get 11.1. Okay, so why are we talking about this? Why are we going back to numbers when I said that this video was about formulas? Well, because this is the same idea that we're going to be using to do this algebraic process. And when I say this, I really mean this part here. Right, so how did we figure out the inverse of 11.1? We set 11.1 equal to our function and we solved for x. And so that's exactly what we're going to be doing kind of more generally. So now we're going to use the same idea to figure out what x would need to be to get any output y. So now we're going to use the same method, and this will probably seem confusing at first, but I think once we go through this example, you'll understand what I mean. So we're going to use the same method to find f inverse of y. So what do I mean when I say f inverse of y? I just mean y just represents like any number. Like we're basically just kind of, instead of taking a specific number like 11.1 and trying to figure out what would be the output for that, now we're kind of repeating that process with just kind of a stand-in number. So what did we do to find f inverse of 11.1? Well, we set 11.1 equal to the function, right? And so how can we do the same idea? Well, we can set y equal to the function. So remember, our function was 2x minus 3. So I'm going to set y equal to 2x minus 3. So what did we do? We set, again, when we were trying to find f inverse of 11.1, we set 11.1 equal to our function and we solved for x. And so that's exactly what we're going to do in this case. We're now going to take y and set it equal to our function and still solve for x. So we're going to go through the steps of basically isolating x. So how would we solve this equation for x? Well, we're just going to try to get x by itself. So we're going to add 3 to both sides. And then we're going to divide both sides by 2. And by the way, I just want to point out that that's exactly what we did here, right? If we looked when we were plugging in a specific number on the right-hand side, how did we figure out what that number was? Well, we added 3 to both sides, right? That's where this 14.1 came from. And then we divided both sides by 2. And that's exactly what we did here. We set some generic number y equal to our function. We added 3 to both sides. We divided both sides by 2. And so now what we basically figured out is that for any number that you're trying to find the inverse of, what do you have to do? You have to add 3 to that number and divide by 2. So this actually is already our inverse function. But the problem is that the x's and y's are kind of switched. We want our function to be a function of x instead of a function of y, because that's usually how we write functions down. And so all we're going to do in this next step is we're just going to switch x's and y's. So we're going to say x plus 3 over 2 is equal to y. And this is going to be our inverse function. So now all we have to do is write this in function notation. So now we can say f inverse of x is equal to x plus 3 over 2. And that is our final answer. So let me just quickly repeat what happened here, because I know this is maybe a little confusing at first. So really all we're doing here is that we are setting, we're setting y equal to our function f of x, and then we're solving for x. And again, if you're trying to understand why, why would you do that? Well, it's just because of what we did up here, right? It's because if you're trying to find the inverse for a specific value, that's exactly what you do. You'd set that number equal to your function and solve for x. We're just doing that same idea, but just with a generic y instead of with a specific number on the other side of the function. Okay, so at this stage, we actually have kind of already found our inverse. The problem is that we want to switch x and y so that it's kind of a more standard looking function. And another way of thinking about it is that, remember that inverse functions have the inputs and outputs are swapped. It's kind of the same idea that we need to kind of switch the roles of x and y, to switch the roles of inputs and outputs. And so what we did here is we swapped x and y. And then the last step we did is we put it in function notation. So we, at the previous step, we had y is equal to x plus 3 over 2. Well, now we just said, okay, we know that this is our inverse function. So let's say f inverse of x is equal to x plus 3 over 2. So if you've learned this method before, which I'm guessing some of you have, you might have learned to swap x and y at the beginning. That is totally fine. You can do that if you want. So another way of doing this is from the very beginning, switch x and y, and then solve it for y instead of for x. You'll get the exact same answer. It just means your x's and y's you're switching them just at a different moment. I personally like to do it this way because of this above, because I think it kind of links better with the understanding for that. It doesn't matter to me when you switch x and y, just as long as you're solving for the right thing and switching them at some point. The other thing I want to point out is that, well, we already did this example, right? So we already found the inverse of 2x minus 3 earlier in this video. So I want to go back to where we did that. So that was the linear function. So, oops, where was that? Here it is. So we found the inverse of 2x minus 3. And remember, we found that it was x plus 3 over 2. And that's exactly what we found here, right? We got x plus 3 over 2. So we got the exact same answer. And the other thing I want to point out is that how did we find the answer when we did it this way? Well, we kind of focused on reversing the steps, right? So our reversal of steps was adding 2 and dividing by 3. And if we look back at how this version panned out, that's actually exactly what we did, right? So what did we do? We added 3 and then we divided by 2. And that's where our inverse function came from. So even when you're using this algebraic method, it is still actually reversing the steps. It's kind of forcing you to go through those motions without actually explicitly writing them down. You're still reversing those steps. Okay, I want to do another example, another couple examples. So this next example will be another one that we already did earlier, just to really see how it works. So let me make sure that I'm copying the right one. Yeah, let's do square root of x plus 4 minus 3. So square root of x plus 4 minus 3. Okay, so how are we going to do this? We're basically just going to take our function and set it equal to y instead of g of x. So we're saying y is equal to the square root of x plus 4 minus 3. So the idea is that instead of setting a specific number equal to the function, we're setting in y, we're plugging in y as like a placeholder. And then we're trying to solve for x to figure out what value of x would give us y as our output. So what are those steps? How do we go about solving this for x? Well, first we would need to add 3 to both sides, right? So we'd get y plus 3 is equal to the square root of x plus 4. So what would be our next step? Well, to get rid of the square root, we have to square both sides. So we get y plus 3 squared is equal to x plus 4. And then what's the next step in isolating x? Well, we need to subtract 4 from both sides. So we get y plus 3 squared minus 4 is equal to x. And so by the way, notice again that we're reversing the steps, right? The original function, you added 4, took the square root, subtracted 3. Here we added 3, we squared, and then we subtracted 4. So it's already kind of doing it for you. It's reversing the steps for you. And so our next thing we need to do is we're going to switch the roles of x and y. And I'm going to also just switch the direction that it's written. So I'm going to rewrite it as y is equal to x plus 3 squared minus 4. And then that means that I can rewrite it in function notation. So g inverse of x is equal to x plus 3 squared minus 4. And then we do have to add that domain restriction. So we already found that earlier. We said that x had to be greater than or equal to negative 3. So if you check what we got earlier, this is exactly the same as what we got when we did it with the reversing the steps method. So set the function equal to y, solve it for x, switch the role of x and y, and then write it in function notation. Okay, so we're going to do one more example, and this is a tricky example. So this is the one that I wrote down earlier. So this is one, I think most people can do the algebra okay for these last two. Maybe you're not so used to solving an equation with 2 variables in it, but the algebraic steps are not so hard. You're just kind of moving things to one side to try to isolate x. This next example, if you don't practice it, you're not really going to know how to do it on your own. So this is a really important one to pay attention to, and you basically just have to practice and learn how the process goes. So our original function is going to be x minus 2 over 3x plus 1. Okay, so the initial steps are going to be exactly the same as in the last two. So we're going to start by setting our function equal to y. So we have y is equal to x minus 2 over 3x plus 1. Okay, so remember that our goal is to solve this for x. And so what is kind of in the way of us solving for x right now is that the x's they're in the numerator and the denominator of this fraction. And so what we want to do is we want to start by breaking down the fraction. So we're going to multiply both sides by 3x plus 1 in order to get rid of this fraction. So we have y times 3x plus 1 is equal to x minus 2. Okay, so again, our goal is to solve this for x, And so we still have some stuff kind of in the way of that. So what we want to do is we want to distribute on this left-hand side because we can't access this x yet, right? In the previous step, we couldn't access these x's because they were in the middle of a fraction. Now we can't access this x because it's within these parentheses. And so we just want to break everything down. And so we can write this as 3xy plus y is equal to x minus 2. Okay, so now everything is completely broken down. So now remember, our goal is to isolate x. And so our next step is we're going to move everything that has an x in it to one side and everything that does not have an x in it to the other side. And so at this point, you have a choice. You can move whatever to whatever side as long as the x's are all on one side and then anything that does not contain an x is on the other side. So I'm going to choose to subtract 3xy from both sides. So I'm kind of moving the x term to the right side, and then I'm going to add 2 to both sides. And so the adding 2 is going to move the 2 to the other side. And so what we're going to end up with is y plus 2 is equal to x minus 3xy. So again, the important thing is that anything that has an x in it needs to be on the same side, and we'll see why in a moment. Anything that does not have an x in it should be on the other side. So you might be a little confused why, well, this one has an x and a y. As long as it has an x in it, it goes on the side with the x's. Everything with an x in it goes on one side, everything with no x in it goes on the other side. Okay, so this is, I think, this next step is really like the key step. So again, what's our goal? Our goal is to solve for x. So what could we do on this right-hand side that would get us a step closer to solving for x? This is tricky. This is, I think, the trickiest step of this whole thing. So what we can do is we can factor out an x on this right-hand side. So let's factor out an x, and let's see what we're left with. So when we factor out an x, we're left with 1 minus 3y. Right? Because if you were to multiply the x back in, you'd get x minus 3xy. And so now what can we do? Well, now that we've factored out this x, again, what's the goal? The goal is to solve for x. And so we're trying to get this x by itself. How can we accomplish that? Well, now we can divide both sides by 1 minus 3y. And that's basically it. Now all we have to do is the normal part of this, which is we're going to switch the roles of x and y. And then we're going to write it into function notation. So h inverse of x is equal to x plus 2 over 1 minus 3x. And that is our inverse function. So let me just write out the steps of this a little more explicitly. So when you look back at it, you can see where everything comes from, and I'll kind of talk through it again. So the first few steps are basically to break everything down. So I'll kind of put that in quotes. And so what do I mean when I say break everything down? I basically mean get rid of the fraction, and then you're going to distribute. So you're basically freeing up these x's so that you can actually do stuff with them. And so what's this next step? This step, we're moving all terms containing x to the same side. And then all terms that don't contain x, those should all go to the other side. So next, what you're going to do is you're going to factor out an x, because everything on that side has an x in it, so you can factor out an x. And then the last thing you're going to do is solve for x. And then from here, it's the same as the other ones. So like I said, this, I generally don't like to, give you a list of like rules that you have to do, but this just is a specific type of function that I think if you don't know the process for how to solve it, you're not really going to get there just by kind of reasoning. You really do have to be aware of how this process works. Okay, so there's one last thing I want to talk about in this video, which is basically a way of checking whether two functions are inverses or not. So in general, if you have two functions, f of x and f inverse of x, and those two functions are inverses of each other, then it's always going to be the case that the following are true. So this is going to go back to composition that we talked about a few videos ago. So f composed with f inverse of x is going to equal x, and f inverse composed with f of x is equal to x. So what does this mean? How can we kind of interpret this? It's basically saying that the inverse function and the original function, or the inverse functions of each other, they cancel each other out. So I want to show you an example with numbers, and then we'll see an example with formulas. So for example, let's say that we have the function f of x is equal to x cubed, and the function f inverse of x is equal to cube root of x. So as we talked about earlier, f of 2 is equal to 8, and f inverse of 8 is equal to 2. So let's try to do both of these kind of compositions. So let's say that we're trying to calculate f composed with f inverse of 8. So this goes back to how this composition works. Remember that this means f of f inverse of 8. So what is f inverse of 8? Well, f inverse of 8 is 2, right? We have that written just above. So f of f inverse of 8 is the same thing as f of 2. I'm just replacing f inverse of 8 with 2, right? Because we know that f inverse of 8 equals 2. And then what is f of 2? Well, we also know that f of 2 is equal to 8. And so notice what happened is that the number that we started with, 8, we came back to 8, right? We did an inverse, and that inverse took us away from 8, but then we reevaluated the function and we got back to 8. So the important thing is that whatever is your original input in the function, once you do the composition, you get that same number out as your output. And let's try it the other way. So if we now do f inverse of f of 2 is what we're going to do. So f inverse of f of 2, well, another way of writing that is f inverse of f of 2. And so what is f of 2? Well, we know f of 2 is 8. So we're calculating f inverse of 8. And what is f inverse of 8? Well, f inverse of 8 is 2. And so again, notice that the number that we initially plugged in is exactly the number that came out. So why is this happening? Well, basically because of the inverses being these reversals of each other, right? If you kind of apply a function and then do the reverse of that function, of course, it's going to take you back to your original function. So let's see what happens if we do this with x. So now let's say that we're doing f composed with f inverse of x as like a formula. So that would be f of f inverse of x. So what is the formula for f inverse? Well, it's cube root of x, right? And so we'd be doing f of cube root of x. And so what does the function f of x do? Well, f of x is the cubing function. So now we have the cube root of x cubed. And so what's the cube root of x cubed? Well, it's just x. So again, whatever you got as your original input, it matches with the output. And I'm just going to underline that because that's really the point here, is that when you do this composition, the original thing you plug in is the same as what you get out. And that happens regardless of whether you're plugging in a number or if you're just doing this with a formula. And so just for the sake of time, I'm not going to do it the other way, but I would encourage you to try f inverse of f of x. You'd get the same thing. So let's do one more example that is a little bit more interesting with this. So let's do one of the ones that we had earlier today. So we're going to do one of the slightly more complicated things. So we had the function h of x is equal to, or actually, what did I call it? I think it was k of x. Let me just check. Not that it matters that much. So this one. So k of x is equal to square root of x plus 4 minus 3. And if you recall, the inverse function came out to be x plus 3 squared minus 4, and then there was a domain restriction. Although the domain restriction is not really going to come into play here. So this is going to be a little crazy, but I do want to just kind of go through it and see what it looks like if we try to compose the function with its inverse. So this is literally just the exact same thing that we did with composing functions. It's just that the two functions we're composing happen to be inverses of each other. Okay, so let's see what happens. Again, now we're going to have k on the outside and k inverse on the inside. So this means that we're doing k of x plus 3 squared minus 4. I know this probably is going to seem a little crazy, but let me just remind you how this works. So when we're evaluating k of some kind of complicated expression, all that means is that anywhere that we see x in our original function, we're just going to replace it with this whole thing. So we're going to replace x with x plus 3 squared minus 4. So we're going to go into our original function for k of x. And everywhere we see an x, we're going to replace it with this whole input that I underlined in orange. So that means we're going to have x plus 3 squared minus 4 plus 4 minus 3. So let me just emphasize where all this came from again. So this part came from the input, right? We were inputting x plus 3 squared minus 4. And then where did all this other stuff come from? Well, that's just the formula for k of x, right? K of x says you take your input, you add 4, you take the square root, you subtract 3, and that's just what we're doing here. So let's see how this all simplifies when we kind of distribute or multiply, move things together. So here we would get the square root of x plus 3 squared, right? Because the 4s are going to cancel out, minus 3. And then what happens when you take the square root of x plus 3 squared? Well, that's just going to be x plus 3. Normally, it would be plus or minus x plus 3, but because of the domain restriction, we don't have to worry about that. And don't worry about that too much. Just, conceptually, the idea is that the square root and the square are canceling each other out. And then we still have this minus 3, right? We have x plus 3 minus 3. And so what does this simplify to? Well, this simplifies to x. And so it worked out exactly as it was supposed to. When you take the original formula and you compose it with the inverse functions formula, what happens is that everything kind of simplifies and cancels each other out, and you're just left with x. And if you think about it, it makes sense, right? Because again, we're taking these functions that are supposed to be reversals of each other, and we're kind of doing one of them to the other. And so they're going to cancel each other out, and you'll just be left with x. So, why am I telling you this part? We already know how to find the formula for an inverse. Well, this is a good way to just check whether things truly are inverses of each other. And plus, it's a nice connection going back to composing functions to understand how there is some special relationship with inverse functions. All right, so in our next video, like I said, we'll be focusing on the graphs of inverse functions. So that is going to be a shorter video. So I know this one was a little longer. Thank you for bearing with me. Please check out the worksheet, and I will see you all in the next video.